So today we're looking at solar resources as part of the overall energy resources we have available to us. And today we're going to look at the interactive map of how to create maps to find out exactly how much radiation and solar energy is available to us to utilize to meet some of our energy needs. It's a little bit difficult thing to calculate because there are so many variables that the amount of radiation depends on. It depends on where you're located on a map, what latitude, longitude you're located. Both from altitude makes a difference, time of year makes a difference, panel mounting and orientation of that mounting makes a difference. Two-axis tracking, always facing the sun, is the best. We can fix the panel, which is the cheapest way to install them, and tilt them up toward the equator at a fixed angle. That means if we're in the northern hemisphere, we're tilting them up to the South Pole. If we're in the southern hemisphere, we're tilting them up from the flat horizontal surface toward the North Pole. And we can also have fixed horizontal mounting, flat on the ground, or we can have vertical mounts on the sides of buildings. Again, just to remind us what we saw last time, this is what we're talking about here, and the tilt angle that we're talking about is this one right here. This is the tilt angle that we refer to, and this diagram is written for the northern hemisphere because it talks about tilting it to the south, and you only want to, that's going to hurt you if in the southern atmosphere and you tilt it to the south. So, but it's drawn for the northern hemisphere, U.S.-centric, in other words, because it's done by the National Renewable Energy Lab of the U.S. Department of Energy. So we can refer back to that if we get confused about some of these choices that we're going to make. Now, we're going to use an interactive map that they have, interactive website. It produces a map such as this, and to show you what we're going to get. And each one of these dots on this map, by the way, represents an experimental data point. In other words, they have solar radiation at all of these points, and they use that to correlate the data, and so the map corresponds with that. And this is the scale that tells us what the colors represent. In other words, this yellow, of course, means that on an annual basis, this one is done on an annual basis, creates 5 to 6 kilowatt hours per square meter per day. And in this area, it's the light green. So it's 4 to 5 kilowatt hours per square meter per day. But now, that's not every day, obviously, is not going to be that. Winter's going to be less than different than summer. But on an average basis, cloudy days will be less than sunshiny days. But on an annual average basis, that's how much solar energy will strike a square meter, about 10 square feet, on a daily basis. Kilowatt hour is 3,413 BTUs per hour if you want to convert that. So that's what we're going to create here. And another example, this one is the last one. This one is, I didn't mention, is the tilt angle is tilted up to the south, being in the northern hemisphere of the U.S. at the latitude and an annual basis. The next one shows it for a two-axis tracking situation where we're always facing the panel toward the sun, and we're looking at the best month. So I took the best situation here. And you can see that from the scale that we're receiving a lot more energy in July. And if we want to pay for the extra cost of a two-axis tracking mechanism, we'll have a lot more energy striking our collector that we can hopefully convert to something useful. And all in the south, you can see it's around 7 to 8 kilowatt hours per square meter per day. So you can do your trade-offs and determine whether it's worth your while to pay for a two-axis tracking system. But things are much more uniform across the country if you do a two-axis tracking situation, as you can see here. Out here, even in the Northwest, you're out there at the high point of 10 to 14 kilowatt hours per square meter per day. Those are the maps that we're going to create here, and we do that by using an interactive online map. And this is the link right here. Whoop, get it in a minute. This is the link, and I think if you click on it, we'll have it come up. Okay, when we go to that link that's on that slide, this is where we're directed to. And as you can see here, we got several choices that we need to make. We need to select the data type. Do we want the average, the minimum case, or the best case? The next, we can choose the month, what month that we're interested in, or we can choose the annual average, which is usually I pick, but let's see. Here we go. What's clicked here is January, and what I showed you before was the annual average for all of these months of the entire year. And the first map that I showed you was for a flat plate down here, tilted south at latitude. Tilted south at latitude. So we go down and we click View Map to see what it looks like, and this is the map that I showed you before, and that I'd already had run. So you can create your own situation. If we go back to create the second map that I mentioned, we can look at July, and July rather than the annual average, which is the best month. We can also look at some of the worst months, being, say, January, if we like, and look at the single axis, not single axis, but two-axis tracking flat plate. Now let me just mention here, it's got two choices, two-axis tracking concentrator and two-axis tracking flat plate. The reason there's a difference is because the concentrator will only reflect and concentrate at the point you want it, the direct radiation coming directly from the sun. There's some diffuse radiation that's coming from the atmosphere that gets scattered as the sun is coming through the atmosphere, which so there is less energy coming as direct radiation that a concentrator can deal with than if it's a flat plate. So if that's the reason there's the difference there. But there's the difference between a concentrator and a flat plate. Here we're talking about a flat plate is what I've been talking about. So that created the high side that had all the red on it, using a two-axis tracking flat plate and looking at the 1 month of July. And if I click View Map, I come up with the map that I showed you before, where it's more uniform across the country, much higher radiation intensity per unit area, with the scale down here shown, goes from 10 to 14 out here in the west, down to the tan, which is about 7 to 8 over here, all up and down the east. So there's some real advantages to being tracking, and of course being in July. We could look at that. Let's just look real quickly at what it looks like for annual average if we do a two-axis tracking. We go back and return to menu, and we go down, and look at annual average rather than just July that we just looked at. And we'll do the 2-axis tracking. 2-axis flat plate again. The only thing I've changed from the previous case was annual rather than July. And in that case, you can see that the annual average is significantly higher out here in the southwest. So there's some real differences in the characteristics of the amount of radiation that's available to you depending on where you're located. So that's the interacting map for the U.S. and I hope you find it beneficial. And by the way, if you click the PDF version that up there at the top, it will create a before you do. I got some software problems on that, but you can show it as a PDF and download it, and it's a little cleaner picture. But that completes the interactive solar map that shows you how to determine how much solar energy is available to us in different situations in the U.S. at least, and there are means to do that also any place in the world. Okay, thank you.